Welcome back, everyone. Now we're going to talk about smart contract vulnerabilities. Okay, here's the syllabus. We're going to talk about 7 different types of attacks. First one is the infamous reentrancy. And the second one is the transaction order-dependent attacks, which is specific for blockchain. And third one is integer overflow and underflow. And the fourth one is the one we just mentioned previous, is the transaction origin. And the fifth one is denial of service attack. And the sixth one is misuse of low-level functions. And the seventh one is floating point and precision. And last, we're going to introduce our company's product, Vulns, which provides automatic security audit and formal verification for smart contract. First, reentrancy. So what is reentrancy? Ethereum solidity is a dynamic language. The contract has the ability to call and use code from external contracts, which is only known in the runtime, not during the compile time. These contracts can typically manipulate Ether and often sending Ether to various external user addresses. The operation of calling external contracts or sending Ether to external address requires contract to submit external calls, and it could be hijacked by malicious actors to alter the function flow. For example, a fallback function forces the contract to execute further code, including a call to itself, so that the code can be repeatedly called again and again, and that's the source of reentrancy. This type of vulnerability was exploited in the famous DAO hack. It happened in 2016 and was one of the earliest hacks in this ecosystem. Afterwards, we're going to see the modern examples of reentrancy. Reentrancy has not faded away. There are other complex Ethereum standards, such as ERC 1155, that support the callback feature, or the ERC 721, which is an NFT one, also supports own call, own receive kind of thing. And the attackers can define their own logic and hijack the business logic. The example on the left is vulnerable code. Specifically, the function at the bottom, function withdraw, is vulnerable to reentrancy. On the second line, require, it uses message.sender.call value, which uses call value to send gas and passing transaction flow to potentially malicious contract. And the call.transfer will transfer enough gas for attackers to proceed whatever his malicious intent is. Another one is the balance, the third line, balance message.sender is updated, modified after the fact that the transaction flow has been transferred to the attacker. So in this case, the attacker can, so when the transaction flow is passed to attacker on the second requirement, require statement, the attacker can re-enter the function, withdraw again, and because at this time, his balance was not updated, so he can withdraw the money again and again until all money in this contract is drained.
So you mean simultaneously calling twice?
Simultaneously, yes, because it's within one transaction.
Within one block?
Within one, it's one transaction.
One transaction.
Yeah, because block includes lots of transactions. In this transaction, flow goes like this. So first, attacker call withdraw, and then it pass a require statement, and then the function flow transaction flow will go to the attacker's malicious contract, and then the contract will call again, withdraw. And because at this stage, the balance was not deducted, so the contract thinks the attacker has enough money.
Okay.
But in fact, he's already done one-time withdrawal. Yeah. So So this is a proof of concept, how to attack this contract. This is the same contract we saw before. It's vulnerable. And this is attacker's contract. First, attackers, they import this reentrance to get symbols. And then it get ether, so it means it deposit, right? It has to have some balance first, so it deposits some money to this contract. And then the main attack function is function called attack. It will withdraw. It will call the withdraw function here. And when this function flow goes back to the attacker called .value, it goes to the fallback function, public payable fallback function. So this function right here will call the withdraw again. And it's in the case if the remaining balance is more than 1 ether, because it wants to get all the money from this contract, right? So when this instance withdraw was called again, then it'll go back to the fallback over and over again, and it'll call back just like that until the balance is less than 1 ether.
What is a fallback?
A fallback function is a function that has no name, and it's payable, so it means that it can accept ether. In this case, the victim contract sends ether to attacker's contract. It means it's accepting ether. And because it's called .value, it will invoke the fallback function automatically. Yeah.
Is the attacker inserting that code to make it do that, or is it already there and it's just the attacker's turning it on or exploiting it?
This contract was completely developed by the attacker, right? So attacker can write his own fallback function.
Okay, so they are inserting this into the blockchain, right, to make
Yes.
the attack.
Yeah. So attacker has to, for example, deploy this contract first and then carry out the attack. And in this case, the code was not originally in this victim contract, but just the victim contract withdraw function is vulnerable.
Okay. So the victim's code wasn't written correctly, and the attacker's written something that can exploit that
Yes.
badly written code.
Yeah, exactly.
So if the call.value function is a default function that does not need to be defined?
It's a default function.
Okay.
Yeah.
So it is somewhat vulnerable because you could just trigger the fallback on this one.
Yes. And worst of all, it passes the remaining gas to the attacker's contract.
Okay.
Because if the attack contract does not have gas, he cannot call back. He does not have enough resource to call back.
So it's only taking gas.
Yeah. For example, we're going to talk about a transfer function. So compared with call.value, transfer function only sends 2,300 gas. And that's not enough for attackers to call back and drain the contract.
Oh, so it's better.
Yeah, better in that sense. But yeah, reentrancy is not that. There are other ways that can cause reentrancy.
So can you explain how the callback function is triggered again?
The callback function
Yeah,
here.
how is it triggered there?
So in the second line, require message.sender.call.value. This line will, in this case, message.sender is the attacker's contract. So it will call the message.sender's fallback function. Because this call.value does not have a function name, it goes to a default fallback function.
Got it. Okay. Understand. Thank you.
Okay. Any other questions?
So,
Yeah.
so the only way to circumvent this is to audit the contract, right?
Yes. Yes, it's recommended to audit the contract because inexperienced developers can make mistakes many ways. And this is not the only way that reentrancy can occur. Yeah. Also, we use formal verification. That means it goes down every single code path. And if it causes state variable to change it in an unexpected way, we can alert the developer. And that's the formal verification. It uses mathematical models. Yeah.
If the fallback function has such vulnerability, why would solidity design has this fallback feature in place?
Fallback is actually very useful because sometimes you need the callback.
When there is no function definition.
Yeah, exactly.
You just want this fallback to
Yeah.
be triggered.
Yeah, and also some logic actually involves the callback. For example, for example, in some NFT, after you receive an NFT, you send out like some other business logic, and then in that case, the only viable way is you have a fallback function. Yeah. But in this pattern, it's not actually very common anymore, the call.value. Right now, the callback is actually more specific. For example, this callback for example, flash loan, solidity flash loan is actually same mechanism as callback, but you define it with a different name, and they have different interface, but the mechanism is still the same. If this mechanism does not exist, then there will be like a loss of functions in many aspects.
So the way to avoid
Yeah.
this situation is, first of all, do not use call.value, right?
Yeah, we're gonna talk about it now.
Okay.
Okay.
So basically, the default visibility of the functions are public.
Default.
The default, yeah. So the default visibility of these functions are public. So
Yes.
attackers, if you don't have a visibility specifier,
Yeah.
then people can
Yeah.
leverage on that. Okay.
But in this case, if withdraw, so imagine this contract is a vault, so people have to be able to call this to withdraw their money. And there are 3 ways we can prevent reentrancy in this case. First, we can use transfer instead of call.value, because transfer only sends 2,300 gas, and that is not enough to call another contract. And we can use checks, effects, interactions. In this case, the balance message.sender is deducted after the money was sent to the user, the withdrawer. But it's better to withdraw this, to modify this balance before the second statement, before the second required statement. In this case, if the attacker re-enters the function, then the solidity contract will know that he does not have balance anymore, and he cannot drain the contract's balance. So that is the checks, effect, interactions. To put it more generally, we have to ensure that state variable changes occur before Ether is sent. And it's the officially recommended model by Solidity of community. And then the third one is use mutex. OpenZeppelin actually has a reentrancy guard template. You can use it to have a mutex built into your contract. For example, in this one, you can have a state variable here and says if the contract is in execution or not. When the contract is in execution, we can lock this contract to prevent re-entrant calls. And just, it is kind of abstract, but I'm going to give an example. For example, we can put a we can put a uint flag equals 1. And if the contract is locked, then we put it to 0. And when the flag is 0, we cannot proceed. So that means this will prevent attacker from calling back to the contract.
What about two users trying to interact with the same contract at the same time? Does it auto prevent that?
Solidity is linear. So when you do this transaction, then transaction is one by one. So when the transaction finishes, then the state will recover.
Okay, so it does not allow
Yeah.
parallel processing.
Transaction order is being determined by miners. So for example, when 2 users call, 1 user has to be behind the first one.
I see.
Next, we're going to talk about transaction order dependent attacks. And this is actually the principle of MEV bot, those front-runner bots that can take profits from trades, for example, like sandwich trading kind of thing. And it's really specific for blockchain. Blockchain transactions, Ethereum transactions are considered valid only when validators include them in a block. It is validators now because Ethereum is now POS. It used to be miners. And miners or validators, they can be bribed. If you initiate your transaction with a higher gas price, then only the transaction with higher gas price will be included, not the one with lower gas price. That's how you can modify your transaction. And for example, if your transaction is not included in the block for a long time, you can accelerate it by putting a higher gas price. But there's a potential attack vector here. if an attacker observed the transaction pool or mempool for transactions, and if he saw a transaction that could benefit him somehow, he can copy this transaction and put a higher gas price and have it included in the block before the original transaction. For example, this attacker can take data from the transaction and have, and we'll have an example of a game that try to guess a number. So this contract name is find this hash. We have a hash here, and we're trying to get the string to result in this hash. And we all know, like, dehashing something is very difficult and requires tremendous computing power. For example, when user solves this challenge, he can get 1,000 Ether. The attackers don't have the computer power to solve this challenge, for example, but he's smart. He observed the mempool, and then he saw the hardworking user who actually solved this challenge, trying to include his transaction in the blockchain. And the attacker saw that in the mempool, and he checks if the answer is correct or not. And if he knows the answer is correct, then he can just submit his own transaction with the string, because it's all public. It's just it's a parameter passed in a function. He can submit his own transaction, but with higher gas price, and that he will beat the hardworking user and get the reward. Yes?
It's like hijacking.
Hijacking, kind of like front running. Yeah. So the transaction order dependent attacks happen because of two factors. First, users can increase gas price. And then validators have the power to reorder transactions. And we have two ways to prevent this type of attack. We can create a restriction in the contract, the gas price cap. This prevents user from increasing gas price and obtaining priority transaction ordering beyond the cap. But it's still not perfect. For example, if we have a gas price cap and the hardworking user doesn't want his transaction be stolen, so he put the highest gas cap price. But if the attacker actually is the validator, then the attacker can still include his own transaction before the hardworking user. A better way would be to use a commit review pattern whenever possible. This scheme stipulates that users send transactions using hidden information. So the user can hash, for example, or encrypt his answer and submit it, and then the contract will decrypt it. This method prevents miners or validators and users to forward-looking transactions. So even when the attacker saw this transaction in the mempool, he cannot just copy it because he has no means to decrypt. Only the smart contract has the power to authenticate that this user actually signed it with his private key, for example, valid signature.
So he cannot decode the content?
Yes. For example, in this case, a string called resolution is passed into the solve function, right? Yeah. So for anyone observing in the mempool, he can get the plain text version of solution. And then he can just submit his own transaction, right?
Yeah.
But for example, if in the second pattern, the commit and review, what if the original hardworking user signed this answer with his private key and submit a signature? Okay. And even if attacker submit this same function, he cannot get the reward because the signature was signed by a different entity. But the smart contract can use, for example, functions like EC recover to verify that it's actually the original user who solved this challenge. And
Will the signature be exposed?
Signature be exposed is fine because it's still it's not related to message.sender. You have to verify signature with the message.sender.
If this is possible, then all the MEV can be avoided now, right?
It's not possible.
Why?
Because in a lot of times, for example, when you're doing swaps, you just want this function to give you back the money. And it's not about a stream, right?
Oh.
Yeah, it's an action. Like I exchange 100 USDC for Ethereum,
Right.
and that's just an action.
So only this text can be hidden.
In this case,
Information you can
yeah, of course, yeah. In this case, it's specific, but MVB bot is not gonna fade away. It's just getting more and more fierce. But you can use other other means to avoid MVB bot. For example, Flashbot, to have your transaction be private until including the block.
So who are the people who have access to the community?
Everyone has access to mempool.
So everybody, not just the validators.
Yeah, everybody can just.
So basically,
Yep.
anyone who monitors it religiously,
Yeah.
spot any
Yeah.
advantage, they
Yeah.
can exploit it.
Yeah.
In the first method you proposed, if two people, two users in the same block
Yeah.
provide the same gas price,
Yeah.
who get priority?
That's determined by the validators. So
Oh.
validators can cheat.
Yeah, he can choose either one.
Yeah. So if the attacker is the validator in this case, then he can still beat the hardworking user.
Right.
So how about using the timestamp to when you submit the contract?
Timestamp is not going to work. Timestamp only updated when a new block is included. When no new block is included, is included, there's no timestamp variable. It's only like how much wait time you have.
The contract, they have a timestamp when you submit. Verification by the miner will take some time.
But different miners have different times, and the only
You have two timestamp when you submitted on the times.
yeah.
And the other is the miner to verify the timestamp.
Miners, for example, they are not that honest. Yeah. They will not say, "Oh, you strictly submitted before the other." They only care about profits. They only care about like how much gas price you're paying, and the timestamp standard is only updated when new block is included. So when you submit the transaction, there's no way to actually use the blockchain timestamp to verify that you actually submitted first. Any questions?
Is
Yeah.
there efforts to
Hmm?
Well,
Yeah.
I was just going to say, is there efforts to make the timestamping functionality at the point of transaction submission? Or is that deemed as not?
I think it's not really possible because blockchain nodes are distributed, they're decentralized, and some of them may have time differences. But only the blockchain consensus won't have the standard timestamp, and that's the authority. So when you submit it, it's really difficult to know because the nodes close to you will receive the transaction first, but when they propagate to other nodes, then the time will be different. Yeah.
Yeah, so you say that the attacker is watching the pool,
Yeah.
right? Sees the most correct or the correct answer, submits it first. But why wouldn't the person that got the correct answer submit it first?
The
That's a stupid question.
the person who got the correct answer already submitted first,
Okay.
but it takes time from when after he submitted and gets included in the block.
Okay.
So attackers utilize this time block to get his transactions included first.
Okay.
Does that answer your question?
So, but how would he do that if the other guy's already submitted it?
Well, you can still submit it,
Yeah.
any transactions, like anytime you want.
Yeah.
The original guy submitted his transaction, but it probably takes like 5 minutes before his transaction will be included in the block.
Okay.
And within that time frame, the attackers observe this transaction and verify the answer is correct. Then,
Is gas price higher? So
Yeah.
Priority.
yes.
Gotcha. All right.
Okay.
Understand.
Any other questions? Okay, so that's how we usually solve it by using a commit and review pattern. And next is a classic integer overflow and underflow. So there's no floating numbers in Ethereum, EVM. It specifies a fixed size data type for integers. This means that each integer variable can only store numbers in the range of fixed size values. in a uint 8, for example, it can only store numbers in the range from 0 to 255. When a variable of type uint 8 has a value of 255 and is added by 1, a rounding error will occur. This will result in overflow and get the value flipped back to 0. So to simply put, the value of solidity integer will change when it is assigned a value above or below the range that it can be represented. Overflow will overflow to 0, and underflow will underflow to 2 to the power of n minus 1. Underflow means when the value is already 0 and you minus by 1, and it will cause this underflow. So based on different types of operation, we categorize the overflow and underflow into 3 types: multiplication, addition, and subtraction. This is a code snippet that's vulnerable. So we can see the uint max is a uint 8. That means the maximum value for max is 255. And so we use the 2 to the power of 8 minus 1, that's 255. But then if we add it by 1, then this overflow variable will be 0, which sometimes is not the intention of developers. So you can see the max plus 1 equals 256, which is beyond the range that uint 8 can represent, and results in addition overflow. This is a subtraction overflow, or I will refer to it by underflow. The minimum value is 0 of uint 8 because it does not include negative numbers. And if you subtract it by 1, it will cause an underflow. This will be the biggest value of uint 8, so 255. The multiplication overflow will behave the same way. Now let's discuss how to defend against this type of bugs. In compiler version later than 0.8, the compiler will automatically check if overflow and underflow takes place. For example, in the contracts at the bottom, we can see that this uint 256x is given a value of 0. And if you minus by 1, this contract will actually not compile because the compiler will detect that there's an underflow happening and will stop the compilation. If we want overflow or underflow to happen intentionally, we can include the code blocks in unchecked curly braces. So if we put unchecked curly braces and put the overflow part in there, the compiler will ignore and think that it's okay. But what if contract uses a compiler version older than 0.8, which is a lot of contracts? There's a library called SafeMath that will help you. You can see we're using the assert statement that will make sure that the overflow and underflow does not happen. We have to be extremely careful. For example, some contracts for compatibility will sometimes use the pragma up there. It's for Solidity compiler version later than 0.7.0, which is vulnerable to integer overflow and underflow. And in this case, we must add the library SafeMath in order to prevent this type of bugs. Oh, any questions about overflow and underflow?
So regarding the compiler time check, so I think if the let's say it's initially run, right, but it only takes like -2 times, then it's still underflow. But this can compile like solve this kind of issue.
Sorry, I don't get your question. Can you repeat it?
So I mean, in the example, because x is 0.
Yeah.
So we cannot like 1. If it's 1, but because we can decrease it for 1 time, but if we try to decrease it for 2 times, it's still underflow.
This x minus minus equals x. Oh, actually, yeah. Maybe I can write it here. X. This equals. So this is the same. So we are only decreasing by 1.
Yes, but I mean, let's say in a function, actually, depending on the runtime situation, we might so the x value might be varies, right?
Yeah.
So let's say this time it's 0, but next time it will be 1.
Yeah.
Let's say it's 1, then we decrease it becomes 0.
Yeah.
Then we try to decrease it again. It's still overflow, right?
Yes, but in this solidity version that's later than 0.8, there's I think there's a third statement that if this thing happened, then for example, in reality the version bigger than later than 0.8 actually adds safe math implementation inside this VM. And when that happened, it will actually cause the transaction to revert. So same as safe math. Yeah.
Quick question. So
Yeah.
what's the use case? How would an attacker make money out of this?
Interesting. So imagine if your balance is 0, and for example, there's a function called transfer. You transfer money to another party, and the balance will be minused by a certain number, by amount that you specify. I have a balance of 0, but I want to get free money. So I invoke the function transfer. And when 0 is deducted by the amount, it causes an underflow. The attacker's balance suddenly got very huge, and he got all the free money.
Okay.
Yeah, this is a simple example of how to use this bug.
Okay. Thank you.
Any other question?
Okay, in reality, I mean, the balance will use like int 256, for example.
Yeah.
So in that scenario, it's difficult to get like overflow or underflow in that scenario.
It's actually not that hard because if it's int 256, you can just make it underflow, right? And for example, a lot of times, like when you have a function parameter, for example, transfer, the amount is determined by user. Users can specify whatever large number he wants. So he can make the number very large and pass it in and make sure the overflow or underflow happen. Yeah, because in Solidity, the balance is actually not really money, it's just numbers. So people can manipulate numbers as they want. Any other questions? Okay, let's continue. Now we're going to talk about transaction origin. tx.origin is a global variable in Solidity that traverses the entire call stack and returns the address of the account from which the initial call was made. Using this variable for authentication in a smart contract can make the contract vulnerable to phishing-like attacks. This type of phishing attack is actually a type of man-in-the-middle attack. So this, I would say, fits more in the line of hijack definition. On the left side is a code snippet that's vulnerable. The contract is called TX user wallet. From the name, we can infer that this wallet might store user's balance. And when the function transfer2 is invoked, it uses tx.origin to authenticate the user and verify that the user actually wants to transfer to some address. On the right-hand side is a malicious contract made by an attacker who wants to perform phishing attacks on user. The attacker's contract name is TX attack wallet, and it has the address owner. And in the function tx attack wallet, the owner will be set to message.sender, which is probably some innocent user that was phished to interact with his contract. And then he will initiate the transfer to the owner address using the message.sender value. In the TX user wallet, the contract will think that the user initiated the transaction and will send the user's balance to the attacker's controlled malicious contract. Okay, any questions? The solution would just be to use message.sender for authorization. TX.origin should not be used for smart contract authorization. It has its own scenario for use. For example, if you want to deny an external contract from calling the current contract, this can be achieved by requiring tx.origin equals message.sender. If this condition is set, that means users cannot use a smart contract to perform interactions with your contract. If a user uses another contract to perform interaction with your contract, then the message.sender will be user's contract, not user's EOA address. To have this statement, we'll rule out all the unwanted smart contract interaction. Any questions about transaction origin? Okay. Now we're going to talk about denial of service attack, DOS.
Sorry, question
Yeah.
on the message.sender.
Yeah.
If you use message.sender, that means your contract only allows EOA address to call it. It does not allow any other smart contract to call it, right?
Yeah, if you have this statement, that means you're denying access to other smart contracts.
Right, but that's limitation of your functionality.
Yes, but for some, for example, high security contracts, they don't want any people to use smart contract to interact with them, right?
Yeah, for example, if I use a smart contract wallet, basically I'm out, right?
Yes, that's the problem. But like most exploits are carried out by using smart contracts.
Yeah.
So if someone is really, really paranoid, he can rule out all the smart contract interaction. Of course, it will affect the functionalities for sure.
Yeah.
So the denial of service attack. There are various ways to perform a DOS attack on a smart contract. The basic purpose of which is to make the contract inoperable for a period of time. With a denial of service attack, the ether of contract can be made permanently unavailable for extraction. There are three types of DOS attack we'll mention here. One is DOS via unexpected revert. Another one is DOS via block gas limit. And another one is operations by owner. We briefly mentioned the DOS via block gas limit at the for loop and while loop. So if the loop is too long and causes too much gas, the transaction probably will never go through, and the contract will be stuck forever. This one is the first scenario, unexpected revert. If the state change of a contract depends on the result of the execution of an external function, and no protection is provided for the case where the execution keeps on failing, then the smart contract may be subject to DOS attack. So in this case, the second required statement is vulnerable. We are sending the bid to current leader. So what if the leader does not accept either? What if he does not have a fallback function? This transaction will never go through. And this required statement will be invoked every time the function bid is called. And other users trying to use this contract, when they call bid, it always fails because the current leader does not accept the ether. And this contract will be stuck forever and not usable anymore. we can add a time-based operation to prevent external function calls from constantly fading. So for example, we can have a time limit. For example, if the block stamp or block number is bigger than number, then this balance of ether will be transferred to, for example, a custodial address, and this will prevent problems like that. But required statement is definitely shouldn't be like that because it depends on the outcome of an external transaction.
So this particular revert attack, is this used by attackers to make money, or is it just bad coding?
It's bad coding because attacker's not making money; he's losing money.
Okay.
Yeah, but for example,
You can't transact.
yeah, this contract is just dead. Okay. So if the attacker tries to, for example, sabotage his competitor, that's a scenario, but he's losing money.
Okay.
Yeah. The second scenario would be DOS via block gas limit. In this example, we have an array of investors. That's an array of address in the second line. And then this vulnerable function is called distribute. We can see there's a for loop. When I is smaller than investor's length, it will loop to transfer tokens to investors. So what if investors' length is huge? That means there are a lot of investors. And this transaction will be like exceeding the gas limit, block gas limit. So this transaction will never get included. And there's no way to distribute money back to investors. There are ways to fix it, and I think most modern-day smart contracts will follow this new pattern. The contract should not loop through bulk operations on data structures that can be manipulated by external users. It is recommended to use the fetch mode withdrawal instead of send mode. This one is a send mode because the contract initiates the sending to users. The fetch mode means that external users, in this case investors, will call withdraw and get their fair share of tokens. In this case, the gas limit will not exceed the block. The gas limit will not exceed the block gas limit. Any questions?
Same question as before. Is
Yeah.
this just bad coding, or is it used by attackers to make money?
This is bad coding because this contract is stuck and investors cannot get their shares.
Understand.
Yeah.
Sorry, I have a question. Can this be used for airdrop? So, exchanges, they want to give token amounts.
Yeah.
So would they do this instead, and as part of the airdrop, would hackers then take this over? Would that happen?
Hackers can take this over. Because if investors' length is too big, then this airdrop transaction will never go through. It's just bad coding on the developer side. So airdrop is recommended to use the fetch mode.
Fetch mode even for airdrop, which
Yeah.
means the users have to be
Yeah.
ready to pull the airdrop.
Yes, exactly. Yeah. And the current, for example, you can see the spammy airdrops. I think they are mostly by scripts. So scripts don't have a gas limit. They can just invoke in a loop. Yeah. But a smart contract, if you code in this way, is really bad practice and probably will cause problems in the future. The third scenario is the owner operations. Many token contracts currently have an owner account, which has the authority to start and pause transactions. If the owner is not kept properly, the token contract may be frozen by one transaction, leading to the DOS attack. For example, if owner is not kept properly, this contract cannot function normally because the global variable is finalized, is set to false initially. Owner need to call the initialize. Owner need to call the finalize function first to set the initialized to true before everything else can function. In this example, the transfer. So if the owner address private key is lost, then this contract will not work anymore. And we recommend set multiple address with owner privilege or set a period of time to suspend trading. It's like time lock in MasterChef. So we can use a request statement like require message.sender equals owner, or null is bigger than unlock time. So if unlock time has passed, then this contract will be activated normally. Any questions about DOS attack? It's not very economic profitable, for sure, as you mentioned. Now let's talk about misuse of low-level functions. Solidity has call and delegate call. The opcodes are very useful in that they allow Ethereum developers to modularize their code. When using the call opcode to handle external standard message call to a contract, the code runs in the environment of the external contract function. It's really abstract, but just know that when you use call, the state of the contract will change. The target in the target smart contract. The delegate opcode is also a standard message call, but the code in the target address runs in the environment of the calling contract. So if you have a contract A and contract B, contract A uses delegate call to use a function in contract B, the state in contract A will be modified. The delegate call will keep the message sender and message.value unchanged. This feature supports implementation libraries where developers can create reusable code for future contracts. And a lot of like proxy contracts will use the delegate call to fulfill their function. Let's look at the call injection attack. This attack is actually very common and probably already caused billions of dollars of loss. We can see here the vulnerable function is transfer from. And it takes in parameters from users. There's no sanitization, and the visibility is public. That means anyone can pass in any values. They can craft any data they want. And in the line here, receiver.call.value. Receiver is an address passed in by, let's see. Yeah, receiver is an instantiated interface of two addresses. Two addresses passed in by attacker. That means receiver is any address defined by attacker. And it uses call.value, which we already mentioned is vulnerable to passing to transfer transaction flow. And it passes in the custom defined data by attackers. This will cause huge problems because attackers can impersonate this contract and do dangerous things in external contracts. Sum up, call is a low-level function provided by Solidity to interact with external contracts or libraries. The use of such functions requires safety of the call parameters. Never trust user inputs, as we say in traditional security. Inappropriate usage can lead to injection attack. Based on what is being injected, there are three types of injection attacks. There are parameter list injection, there are method selector injection, and there's bytes injection. Any questions so far?
So the bytes injection, will it be that bytes for that they inject?
Yeah, for example, the bytes data there.
Okay.
Yeah, because it's custom defined, right? The attacker can craft some bytes. And usually those bytes are further interpreted further down the stack. So we categorize as bytes injection, but it's actually a parameter injection first, but bytes injection later. And how to fix this bug? We should restrict privileged operations. First, we can check if the sender is its own address. And in this way, you can authenticate the function caller. And next, we can use function modifiers such as private and internal to restrict permissions on function. In this case, the visibility is public. But if you put it as a private or internal, the attackers cannot call this function directly anymore. But still, we have to be very careful about the parameters passed in by users. Even calling internal or private functions, those parameters need to be sanitized properly or the user's control variable should be marked specifically to make sure that no malicious data will be passed into other functions as well.
So what's the definition of private and public?
The public means anyone can call this function, and the private means only the functions within this contract can call.
Oh.
Yeah.
So still, it can be called indirectly by the user.
Yes, of course.
Because if there's another function that is public,
yeah.
this public function is calling the private function.
Yeah.
That's still allowed.
Yes, but that's why it's really important to be careful about the inputs, the parameter inputs. Yeah.
Sorry, can you explain again? Sorry, why is that statement vulnerable?
Why is
that statement vulnerable?
This one?
Yeah.
Because receiver is interface ERC 223 interface instantiated on the address of underline 2. And underline 2 is passed in by the attacker. So it can be any address, including his malicious contract address. And, or for example, in this case, I would say, for example, an external vault or external flash loan contract. And then when you call the value of it, when you call the value of it, the data passing is actually attacker's control data. So he can maybe probably like withdraw money or do some other malicious actions.
Sorry, for user control variables, would putting a bounded range or a list of values against those user-defined variables prevent exploits there? So for user control variables,
yeah.
if we say we define a bounded range
yeah.
that only accepts within that range or
yeah.
a drop-down list of values, would that then protect the smart contract against malicious exploit?
Yes, it's the concept of whitelist. Like, for example, if the address, if the address underline 2 is not in the whitelist, then maybe the transaction can revert. That's a use case. But still, you have to be very careful about whitelist. Yeah, there's plenty of problems happening, like with projects already made their own whitelist, because whitelist might be proxy contracts. They might have other functions added in, or if the code in the smart contract in the whitelist was not examined carefully, it might have some other problems. For example, the wrapped ether contract does not support the signature verification. Yeah.
So just following on that, would the whitelist, the list of addresses, would that be in the external file, or is it within the contract itself?
Within the contract itself. It's going to be stored in storage.
So who controls the whitelist and how does it get updated?
Usually contract writer, owner, or deployer. Or it can be a multi-signature address, right? So it can be, for example, if it's a DAO, then it can be the governance address. You have to reach like certain threshold votes and add the contract to the whitelist.
Right. Mm. Okay. So the contract can be updated?
Yeah, storage will be updated.
Yeah,
storage of contract. Yeah. Any other questions? Okay. Now, it's a floating point and precision. As we mentioned before, solidity does not have floating point. And you should be aware when dealing with numeric types. Solidity only has integer division, and integer division loses precision. Any precision smaller than the divisor will be discarded. In the same way that ERC20 smart contracts specify decimals, the smallest unit is also used for specific values. Floating point and precision is usually used in scenarios such as ratio and exchange rates. So they must be dealt with extreme caution. Please have a look at this code and just ignore any overflow or underflow bugs, because it might be vulnerable if the compiler version is older. The code I want to talk about is the second line in function cell tokens. Cell tokens accept the parameter of tokens. So transfer Ethereum to the seller. In the second line, the ether amount equals tokens divided by tokens per ETH. The logic seems okay, but the floating point problem means that the business logic might be in peril, because imagine if token number is 29 and tokens per ETH is 10. The resulting ETH will be 2. The 0.9 ETH will be discarded completely. The seller will be put in a disadvantaged position. And to fix this, we can have a virtual precision number, for example, another int 128 or 256 to represent precision, or we can make it less more damaging by put the multiply operation first before division. And also, it's we have to make sure that numerator is bigger than denominator. Otherwise, it's just gonna get 0 all the time. Any questions? Yeah.
Is this just bad coding, or it actually can be exploited by attackers as well?
In Solidity, no, but in other blockchains, for example, Rust, the precision number can be profitable, can be exploitable. And the reason is the rounding errors. Every token has a decimal, and in Solidity, the gas price is high, and the decimal, and if you just use decimal to get an off by 1 error, the result will not be profitable. But in Solana, it's a different story. In Solana, the gas price is very low, and you can have transaction bundled in a. You have multiple instructions bundled in a transaction, and basically an off by 1 error, the precision error, can make sure that you get 1 token more than the token that you put in. And if the token value is big, for example, if it's a wrapped Bitcoin, then 1 unit of Bitcoin, wrapped Bitcoin is bigger than, for example, the gas that you use. In that case, you can make a script and just exploit the precision error. In this case, it's rather bad coding because the seller was put into a bad position. Yeah. But if there's a buyer, then it will benefit the buyer maybe.
Yeah.
So. Let's see. Yeah. So our company's product is called Vulns, and it's a artificial intelligence, and it will audit the smart contract code, and it also provide the formal verification function. And there are 4 reasons that we developed this product. The first one is manual auditing takes time, and the content is limited, because you have to look at like the modern day projects, their code base is huge, and you have to look through the code one by one, and it takes a lot of human effort, and it's inefficient. Next, there's a lack of understanding in industry standard norms. The Solidity standard, ERC standards are constantly updating, and it's very difficult for developers to keep up with the security aspect of all of them. And for example, there's a ERC 20, ERC 1400, and the ERC 1155, for example, they are vulnerable to the callback reentrancy, and not many people know about it. And the language of smart contract is not unified, and the code auditing is difficult. For example, we just talk about Solidity, but there's actually Go, Java, Node.js, or Rust coded, or even Move coded smart contract. And multiple programming languages make it very hard for a small project to learn the security aspects of all of them. And some industries need to meet smart contract security compliance standards. The formal verification provides a stamp to this compliance. For example, the central bank requires the security specification for financial distributed ledger technology that specifically says that the contract should be formally verified. You can access the product by going to the following URL. So yeah, we provide a static scanning, that is to scan for vulnerable code patterns. We do fuzzing, that is to generate and provide input into different functions and see if the result is unexpected. And we have formal verification. It will explore all the available code path. This product will automatically test of traditional vulnerabilities and business logic correctness. This after we load the contract in the code, it will provide fixed recommendations. And this platform supports multiple blockchains such as Ethereum, BSC, Matic, AAVE, Ontology, and EOS. Here is the list of our scanning add-ons. First, we look at the coding standards. We'll look at the common ERC standards for Ethereum and non-zero address checks, constructor input, and fake recharge vulnerabilities. For example, if the Tether, the USDT token, has this problem with fake recharging because they don't follow the ERC20 standards strictly. And we also test call-off functions. We test possible issues that may occur in calling functions, such as reentrancy. And we also explore business logic security. It's different from project to project. We check the issues that may lead to security risks in business logic, including malicious DOS attacks and permanent call failures, for example. We also check the exceptional status. Our tool can detect exceptional status that may occur during execution of the contract. Of course, contract vulnerabilities. We will detect common vulnerabilities as well as the updated ones. We also can make sure that the authorization bypass is not happening anywhere in the code. This is an example of our tool scanning. So it's difficult to see, I understand, but it's actually to.call.value amount. So we highlight this part of code. And we also give the reason why this code is vulnerable and some external material, and provide ways to fix this vulnerability before you can deploy them in your network. This is completely automatic, so and has the accuracy of up to 97%. And under the hood is basically we compile them into bytecode, and we use, for example, for formal verification on the bytecode itself, not the smart contract code. Any questions?
Yeah. So
yeah.
Is this function supposed to be something you use very frequently during your development work, or is it just mostly like a one-time thing after you develop everything? Because it depends on how much it costs, right? If it's like $10 each time, then I'll probably do it like 3 times a week or 5 times a week because I just use it to check my work, right?
Yeah.
But if it's like $300, then I'll consider you're not using it too frequently, right?
Yeah. This function can be used frequently because it's not. It's unlike human auditing, which takes time and effort.
Yeah.
This one is completely machine-driven,
Right.
So you can use it as many times in your development cycle as possible.
Right.
But to make sure that everything fits well, before your project goes online formally, you should still have manual auditing performed based on the size of your project.
Yeah. But this one is very cheap, right?
This one is cheap.
How much?
How much? I think the subscription model actually is there. I'm not on the sales department, so yeah. But manual auditing is more expensive for sure. Yeah. And also depends on the platform you're developing, right? We also support Rust for now, so and move in the future. And if you want to develop, for example, in Solana or other blockchains, then you can still use this tool. Let's see. Okay. And just an added example. So, yeah, this. So reagency is more complicated than the one that we just mentioned. For example, in this case, last July, this Omni NFT platform was hacked, and it was caused by a reagency bug. The loss is 1.4 million, and ironically, the cost of the bug was ERC 721 safe transfer from method. ERC 721 is an NFT standard, and the name safe transfer from is not safe at all. So when you see this ERC token receiver 2 is an address by anyone. Anyone can input it. So in this case, it's a malicious address, and so you got this. So the transaction flow was passed into the malicious contract. And then it causes the reentrancy into the original contract, and combined with another reentrancy bug in the execute withdraw ERC 721. This is a little bit complicated, so if you're interested, you can contact me in the future. I have the proof of concept for it, and if you want to learn more about reentrancy, there are a lot of materials online. And this is a ERC 721 reentrancy, and on other platform, you can find like ERC 1155 reentrancy, and it's quite interesting. Yeah.
So it actually called out unsafe recipient. So it identified that it was an unsafe recipient.
Well, the required statement means that if this condition failed, then it will get an error of unsafe recipient. But if the attacker implement this interface, if he instantiated this own ERC 721 received interface properly, then it is considered a safe recipient. Okay. Any other questions?
Maybe a generic question. If they say I have deployed a smart contract and I found some function is vulnerable, and then maybe only myself know this, then what should I do?
Are you the project owner or the auditor?
I'm the smart contract owner, let's say.
Owner.
Deployed owner, yeah. So if I found some function is vulnerable and maybe it's not leak out, so what should I do?
Is this your own project or other people's project?
No, just this big question. So
yeah.
So just use people how to approach this kind of issue if they are facing it.
Usually, if it's other people's project, then you can check their webpage, see if there's like a bug bounty. And there's platforms such as like Immunify that you can submit your bugs, and they act like a middleman. And when the project have some bounties, they will send the money to them first, and after it's fixed, then they will send the money to you. And in the Web3 industry, the bug bounty is very lucrative. So it's very common to get bug bounties over $1 million. And I think the highest was almost like $10 million for one bug. So it's encouraged to actually help the ecosystem grow and report them like to the corresponding entities. Yeah.
So my question is, after they found the bugs,
yeah.
how they do with the situation?
Yeah, there are a couple of ways. For example, if you have the pause mechanism coded into the contract, you can pause the contract, right? And you can, for example, withdraw all the balance to a temporary address to protect it. Or you can have, you can monitor. We also provide a service. It's called like transaction interception. Like if you see a malicious transaction in the mempool, you can, for example, increase your gas price and get it before the attacker did, or for example, pause the contract before the malicious operation taking place. And but it's very tricky because on blockchain everything is transparent. If you fix a vulnerability or if you try to like pause it, then everyone knows that your contract is